We're good.
Transition. Okay. So the next speaker is Kent Tobiska from Space Environment Technologies. And Kent will be talking about a specific application using the SDO data in his particular operational irradiance drivers for density, thermospheric density. And now we're switching over to you, Kent.
Great.
And we're waiting. I'll let you know when it comes up.
Great.
There we go.
You see that?
Yep. And now you're in presentation mode. Take it away.
All right, good. Thank you, Rodney and Frank. Let's see. So we have a team over at SET, listed them there: Dave Bouwer, Gupta, Cruz, Kaiya, Wahl, and Sofia Ozambela, working on a lot of our operation stuff regarding taking data streams that we acquire from third-party sources. In this case, we've been using the SDO EVE data for quite some time to help generate irradiance drivers for thermosphere density systems. So the what I'm going to talk about here mainly is what we're doing for the operational thermosphere densities that are related to developing or releasing the NORAD two-line element sets that run over in Vandenberg at the Combined Space Operations Center that's now called Delta II under the US Space Force. There's been progress over the last period of time. I'll just identify a couple things. First of all, there's been a density baseline database released, and also we've identified directions for improvement of all of our operations activities. So I'll review some of that. Here at SET, we create the S10, M10, and Y10 indices. These have been around for 15 years now, I guess. These are used operationally to drive the thermosphere used by Space Force Delta II. It used to be called CSpOC for their NORAD catalog activities. Historically, we've now made available publicly a number of groups, both in the US and around the world, are using this historical HASDM database that's generated from this process. HASDM stands for High Altitude or High Accuracy Satellite Drag Model. It's an Air Force model we helped develop a decade and a half ago. A 2 solar cycle database of the thermosphere densities has been released. It's really the gold standard now. I'll show you some metrics from it in a minute. It's a SQL database, and it's about a half a terabyte of every 3 hours, starting January 1st, 2000, going to December 31st, 2019. 25-kilometer altitude steps between 175 and 825 kilometers, and the latitude longitude bins are 10 by 15. In addition to that, we've looked at some metrics in terms of the forecast capabilities we're doing for our indices. So related to the SDO EVE data in particular, EVE has really been a help for us in our operations. We iterate and connect with the EVE team probably at least once a month, if not more often, on some of the things. This is an example of the S10 index that's created that we do at SET. So those are longer solar cycle timescales, as well as more current data values. So we pull those data down from the LASP database. We have our own algorithm that creates an S10 index, and I'll tell you some of the nuances about it in a moment. The next thing that I wanted to mention is we do also, we're transitioning over to using the GOES 16 data. Here's an example of the Lyman alpha from GOES 16. And that's used in our Y10 index in combination with the GOES 1 to 8 angstroms to create an index that's representative of the energy deposited around the 95 to 100 kilometer region. So let's see. In these data indices, what we do is we use the EVE data from 26 to 34 nanometer bandpass. We create the S10 index out of that. There's a algorithm that we've published for a number of years on that. We're switching over to using the GO16 right now. We already have downloaded it, but we're still doing some calibration issues. S10 contributes about 74% of the total exospheric temperature, the T sub C daily variability in the thermosphere. So it is really the main driver of the thermosphere. And it's the index that's really tuned to the absorption by atomic oxygen, particularly above about 200 kilometers altitude. M10 is, we use the GOM magnesium 2-quarter ring ratio data right now. It's a proxy for the 160 nanometer bandpass, which is a Schumann-Runge continuum far ultraviolet set of photons that come from basically the surface of the sun. And those are very effective at dissociating O2 down at the 110 kilometer level in the thermosphere. The Y10 index is a composite index. It's created using both Lyman alpha and the 1 to 8 angstrom X-rays. Both of those deposit down into the lowest thermosphere, mesosphere boundary, 85 to 95 kilometers, and are instrumental in nitric oxide and water chemistry and energy transfer processes. The main issues we see are that in solar minimum, we see a greater collapse of the thermosphere than what's actually presented by the solar indices. In the modeling, there is no carbon dioxide CO2 cooling, thermospheric cooling that's been postulated starting with Roble back in the 1980s. So our poor man's solution is to decrease the S10 index by about 30% value at solar minimum, removing that energy from the top of the atmosphere. It's not the ideal way to do it, but it works for operations. And I'll show you some of the results in a second. GO16 data has been difficult to extract and use. We're in the midst of doing that, but that's just part of the process. And then we're in the process of calibrating the 26 to 34 and Lyman alpha bands for GO16 to E values and also to our historical databases. I won't go into this in very much detail. I just want to mention that here's a slide. It's available on the Dropbox. This goes through how we create these indices and how they're used by Space Command. But basically, we create the indices. They're then extracted several times a day by Space Command. They then use calibration satellites to also derive density from a number of satellites at different inclinations and altitudes. They take the atmosphere that was created of the JB 2008 atmosphere that was thermosphere that was created by our indices. They modify it using the densities from the calibration satellites in a data assimilative methodology. And then they have a new adjusted atmosphere that they apply to the entire NORAD catalog. And now they get down to errors on the order of 2 to 10% for that 200, 800 kilometer region. Here's examples of that HASDM database. So on the left panel is the Halloween storm in 2003, and then a 2-day database of variability over Boulder and over 0 lat, 0 longitude. A little bit of the uncertainty. You can see that this is for, the top panel is for solar minimum solar maximum in 2001, and then bottom panel is solar minimum 2009. But you can see for a number of these satellites, this is what the HASDM database is giving. It's got right around a 4% at solar max, and then a 4 to 10% uncertainty by altitude for low solar activity. The higher uncertainty occurs at solar minimum because the top of the thermosphere is collapsed, it's less dense, and so the uncertainties go up. but here's a composite slide that shows the same kind of thing, but for both solar minimum and solar maximum and moderate solar activity. The red cross up there, about 400 kilometers at 15% uncertainty. That's what Frank Marcos identified back in about 15 years ago as the lower threshold below which the Kaiya and the EMSIS models could not achieve an accuracy better than that. So you can see that we're really operating down at the very bottom here of the uncertainties compared to what had been historically. So that's been operational for about 10 years now, and that's why for example, they have to move the space station about once a year based on, some of these predictions that we provide. This is an example of our forecast methodology. We simply use persistence and recurrence. It's not very sophisticated, but in these boxes, again, you'll be able to see if you want to download the slides. But if we look at the black lines for on each of these panels, this is for low solar activity in the upper left panel, moderate activity, then elevated and really high activity. And then you can see that for low solar activity, we've got some 4,000 forecasts. So this is based on a West Virginia University group that's gone through and looked at our forecasts and compared it what the actual values were. So the S10, our forecasts even out to 6 days for low activity are pretty good. We're down at a percent or two. However, during high activity, our uncertainties go up substantially, up to about 25% out at 6 days. We do a 6-day forecast with this methodology. For our Y10, same kind of thing. Again, look at the black line. That's the mean percent uncertainty. And again, during low solar activity in this upper left panel, for all these 4,000 forecasts, we get on the order of a few percent uncertainty, whereas it goes up higher during high solar activity.
Empty in about 3 minutes.
Oh, okay, so I'll just finish up here in these next couple slides. Conclusions I'd like to just point out are that we've made a lot of progress over the last few years in operations, providing the DoD and the NASA community with I think a really excellent forecast and current epic of the thermosphere. It's through the HASDM system that's run by the JB 2008 model. For the indices that drive that model, the S10, M10, and Y10 indices, we also use F10 as well. That's incorporated, but we don't do anything with it other than report it. Let's see. We see that there's these issues of the solar minimum thermosphere. It collapses. There's greater energy loss that is represented by change in solar indices, likely due to anthropogenic CO2 thermospheric cooling. It leads to longer debris lifetimes. And so our community, I think, is trying to look at solutions on how to better represent that CO2 cooling. GO16 data, we're still in the process of using that, learning to use it. The Lyman alpha and magnesium 2 quarter ring values still need to be calibrated to SET ops values. We have released a 2 solar cycle HASDM database in the last 6 months. A number of groups, probably 24 groups around the world are using that now. And that typically has about a 1 sigma percent density uncertainty that's down at the 2 to 10%, depends on time of the solar cycle and also the altitude you're looking at. A lot of groups are working on machine learning algorithms, and including our partners at West Virginia University, to be able to characterize the entire database and its variability. High altitude densities need to be understood better, above 500 kilometers, for example, the oxygen to helium transition. And finally, we've completed an initial survey. There's a paper out of Space Weather Journal paper by Licata just at the end of this last year in the fall, identifying what our forecast results are. So we've identified particularly areas that need improvement based on that work. So that's kind of how we've been very lucky to, and I think fortunate to use the SDO EVE data in particular. And it's really provided a fantastic capability for the operations community, even though it's been a science data product. That's all I got.
Excellent, Kent, thank you. And we're still a little bit behind, but I'm going to ask one question because Frank asked the same thing in the chat. What's missing? If you had one solar observation that you could either improve temporal or spatially, or a new measurement that is not being made, what would you ask for?
Yeah, great question, Rodney. So you guys back in the 2000s did an excellent job at figuring out the band passes for the A, B, C channels, whatever, you know, for the GOES instruments. That 26 to 34 nanometer channel really does it. I would say that in terms of the solar component right now, what the system you have built really has the essential elements to it. And in particular, most of the energy is coming from this iron line at 284 and the helium line at 304. And those two are the big components really accounting for most of what we see. So I think where the next improvements come from is really getting a grasp of the far side evolution, the source surface maps, and turning that into a usable forecast. I know Carl Henny's ADAPT model has made really good progress in that area, but I would say that for the solar irradiance side of things, that's really the big thing in the future, is being able to use those kind of far side forecasts to be able to then translate them into irradiance forecasts.
Excellent. Well, thank you. And I think we will now move on to the next